Okay, so let's start. So we are going to wrap up everything this week, right? We are going to put everything together. So what is going to be the final aim? As I said, our aim is to classify, given a P field K, so P is a prime number, right? We want to classify primitive extensions L over K, right? Now, one of the things we have seen is that any separable extension of a P field is automatically solvable, right? That's one of the things we have seen. And we have seen that for an arbitrary field K, a primitive solvable extension is of prime power degree, right? So our primitive extensions, they are going to be of degree L to the n for some prime L, right? So there are two primes. There is a prime P, which is the residual characteristic of our P field K. And then there's this prime L, which is so that L to the n is the degree of the primitive extension that we are looking at. Now, two cases naturally arise in such situations. L could be different from P, or L could be equal to P. So if L is different from P, we are in this thing called the tame case. And we know how to write down all tamely ramified extensions, right? So this is very easy. We have done it. I mean, it's not completely obvious, but we have done it, and everything can be made very explicit. So the interesting thing is the case when L is equal to P, which is to say that we are now looking at primitive extensions of K of degree P to the n, right? Normally the degree was L to the n, but L is equal to P. So we stop using this notation L altogether, and we just look at extensions of degree P to the n. So that's what we are going to do today. So today we are going to so here is the statement. I mean, we'll come to it slowly after introducing the notation. So this I've explained. So we are interested in primitive P extensions of the P field K. P extensions just means that the degree is a power of P. Right? We are interested in primitive P extensions of our P field K. Or, I mean, we could also say wildly primitive, because we have this distinction between tame ramification and wild ramification, right? So what is that distinction? The distinction is, if you have a finite separable extension, then you have the ramification index, and it may happen that this is prime to P, or it's divisible by P. So this, when it's prime to P, this is the tame case, and when it is divisible by P, this is the wild case, right? So we could also call them wildly primitive, because they are primitive and they're wildly ramified. right? I mean, if you have a primitive extension L of a P field K, if it's primitive, then of course it's either unramified. If it's unramified, then it's or let me put it this way, instead of unramified, let's go into this. So let's start with the P field K and a primitive extension. So as I've explained, it could be either tamely ramified or it could be wildly ramified. So if it's wildly ramified, meaning if the ramification index is divisible by P, then it has to be actually totally ramified. So wildly ramified just means that the ramification index is divisible by P. It doesn't mean that the degree of the extension is equal to the ramification index. But if it's primitive, then and wildly ramified, then it will have to be totally ramified. Why is that? That's because you always have this intermediate extension, the maximal tamely ramified extension or the maximal unramified extension of K in L naught. And so you always have this intermediate extension. But if L is primitive over K, then this is either equal to this or equal to this. So if you have equality here, then it's totally ramified. If you have equality here, then it's unramified. And if it's unramified, then of course it has to be of prime degree. So that's the case which is already taken care of here. But if it's wildly ramified, then it has to be totally ramified because there can be no intermediate extension, right? So that's why such extensions are also called wildly ramified. Okay. Right. Now,
Yes, sir.
yes. So what we are going to do today is classify primitive extensions of degree p to the n, right? So for that I need some notation, and then I'll come to the statement of the result, right? So this is the residue field of my p field K. Q is the number of elements in the residue field, and n is any integer n. I'll denote by e sub n the integer p to the n minus 1. Okay, and kn is the extension of k obtained by adjoining a primitive nth root of unity, right? What is that? This denotes an element. So an element such that, so let's call it zeta, an element zeta such that zeta to the power en is equal to 1, but zeta to the power d is different from 1 for every divisor d of this en. That's what it means to be primitive, right? So, so here the word primitive is the use of the word primitive to say that this is a primitive primitive nth root of unity. That use of the word primitive is very different from the notion of a primitive extension, right? Primitive nth root of 1. Here it just means the order of this element is En and not some divisor of En.
Yes, sir. N is the order of this root.
Not N, En, not N. You see, the order of this root
Yes, sir. Yes, sir. Yes, sir.
En, where this stands for an element of order En in the multiplicative group. So you have our K here. We have fixed K and we have fixed an integer N. Then we have this Kn, which is obtained from K by adjoining an Enth root of unity. So En is p to the power n minus 1. And then we have Ln, which is here. Ln is to Kn, we adjoin the Enth roots of everything in Kn star. What is that? That's a kind of Kumar extension, right? This is a Kumar kind of extension because this field, the base field here, has a primitive Enth root of unity, and therefore you can adjoin the primitive Enth roots of everything in the base field, and you get what is called the maximal abelian extension of Kn of exponent dividing En. Right? It has a big name, but it is a simple definition. You just adjoin the Enth roots of everything in Kn, right? So the important thing is that this is our En, this is Kn, and this is Ln. So Ln is here, Kn is here, and K is here. What do we know about this extension? What we know is that it's unramified. But what is the degree? It's unramified of degree equal to Sn. And this Sn is just the so in general, I mean, we have so when I say that Kn is the unramified extension of K of degree Sn, which is the order of the, when I say this, I'm quoting a theorem. And the theorem was what? So it says, the theorem says that if I have a P field K, and D is some integer, and D should be prime to P, then under these circumstances, if I adjoin a dth root of unity to 1, this is a dth root of unity which I have attached, then I get an unramified extension. That's the first thing. And the degree of this extension, dth root of 1, so the degree over K is equal to the order of Q bar in Z mod dz star. That is something which we have already done when we discussed unramified extensions. So for example, let's take a very simple example. Sorry. What is happening here? Yeah. Let us take a very simple example to see. So suppose I take K equal to QP itself, and I take D to be P minus 1. And this is certainly not divisible by P, right? It's prime to P. So what should be the degree of K adjoint dth root of 1 over K? It should be equal to the order of Q. Q here is P, right? Order of P in Z mod dz. So D is P minus 1, P minus 1 Z. What is the order of P in this? But P is congruent to 1 modulo P minus 1, right? So the order is equal to 1. So this degree should be actually equal to 1, meaning this should be equal to this, which is true. I mean, we know that this K contains all the P minus 1 as roots of unity. So that's a very simple example of the theorem that I've just quoted. In general, if I join the dth root of unity and D is prime to P, then I get an unramified extension of degree equal to the order of Q. Q is the cardinality of the residue field. The order of Q in the multiplicative group modulo D. D here is En. Right? Okay, so that takes care of Kn. I know that Kn is an unramified extension, and I'm calling it Sn, the order of Q in Z mod En Z star. So this is of degree Sn. But what's the degree of Ln over Kn? That's very easy. That the order of the degree of Ln over Kn, all of you should be, okay, so you should be able to compute this. It is just En squared. Or to be more precise, what I should say is that, I don't know why it's. I've just said that the degree of Kn over K is Sn, and it's unramified. So that's the same as saying that E of Kn over K is 1, and yeah, it's unramified, right? And F of Kn over K is equal to Sn. This is what we know about this extension. How about the extension Ln over Kn? What do we know about its ramification index? We know that this is equal to En. What do we know about the residual degree? That's also equal to En. And that comes from this. This comes from the structure of what's that? Kn star modulo Kn star to the power En. Right? We are doing Kummer theory here. Okay, so if we put these two things together, we get that the ramification index of Ln over K is En, but the residual degree of Ln over K is Sn times En. That's what is said here, finally. So this is the ramification index is En, and the residual degree is Sn times En. Right? Okay. So you should have no difficulty in, I mean, of course, you have to recall what we had done earlier, right? Fine. Now, this Ln over K, so that's also Galois. We have Ln over Kn is Galois, Kn over K is Galois. That normally doesn't imply that that this tower, I mean, that ln over k is Galois, not in general, but in this particular case, that is true. That's true because ln is the maximal abelian extension. Ln is the, I mean, it is obviously separable over k because this is separable and this is separable. The only question is whether it is what is called normal over k, and it's normal by its, more or less by its maximality. I mean, it's the, right, the maximal abelian extension of Kn of exponent dividing En. So it's going to be normal over K, and therefore it's Galois over K. So it's Galois over K, and we have various Galois groups here, right? What are the Galois groups? So they are given some names. You have ln, sorry, ln, Kn, K. This group is being called T. This group is, but T is, no, it's not being called T. No. Careful. You see, what you have, so in fact, we have the following tower of extensions. You have K here, then you have Kn here. This is of degree Sn, unramified of degree Sn. Then here is something that I might call Ln0. And then you have Ln. So this is the maximal unramified extension of Kn in Ln. Right? So this is ln over Kn. This is what we had earlier, but it's not, here it was unramified. But ln over Kn is not unramified. It's not totally ramified. There's a bit of ramification and a bit of unramified part. So that is what we have to look at. You have ln here, the maximal unramified extension of Kn in ln, which is ln0, and then you have K. So T is this is unramified, right? And this group here is T. This group here is Gn modulo T. And of course, the whole group is Gn. So Gn is the Galois group of ln over K. That's the, no, not this one. It's this big one. And then T is the inertia subgroup. So that's the inertia subgroup. And inertia subgroup means that you take the maximal unramified extension inside this, and then you is the Galois group of this part, right? So that is T. That's the inertia subgroup. And goodness. Okay, so you have this exact sequence, this short exact sequence, right? But the thing is that this exact sequence splits, meaning it has a section. So you might ask why it splits. And I leave it as an exercise. I think one of the things you can say is that, so the hint is you have Kn over K, and how is ln obtained from Kn It's just by obtaining, I mean, I normally said you take the nth square root, nth roots of everything in Kn star. But you don't have to take the nth roots of everything. You just need to take the nth roots of two things. Namely, so ln is equal to kn, to which you adjoin an nth root of u and an nth root of pi kn. Now, where u is a unit, I mean, it's enough to take u in O kn star, which such that u bar, which is an element of the residue field, the multiplicative group of the residue field, Kn. This is a cyclic group, so you want u bar to be a generator. So the first thing should be a generator, and the second thing should be the nth root of a uniformizer. But because Kn over K is unramified, I can take pi Kn to be equal to pi K. A uniformizer of K will continue to be a uniformizer of Kn, because this is unramified. So that's one of the reasons why, that's the reason why I can assert that this sequence splits. So there are some equivalent ways of expressing that this sequence splits in the sense of having a section. And one of the equivalent ways is that you see, okay, I think we have done it when we discussed tamely ramified Galois extensions and when they are split. So you just go back to that discussion and you will see that here in this case, we have the requisite conditions are satisfied. So this is this short exact sequence here splits. So another thing to notice is that if our P field has characteristic 0, then this ln star has a primitive pth root of unity. Why is that? Because you'll notice that this ln contains L1. Ln is you are extracting enth roots. L1 is when you are extracting e1th roots. E1 is p minus 1. En is p to the n minus 1. But because p minus 1 divides p to the n minus 1, if it contains an enth root of unity, then of course it contains an e1th root of unity. Wait a moment. I don't want to be e minus now. So what I want is, let me see. So, okay, let's put it this way. I mean, see, this is the maximal abelian extension of exponent dividing p to the n minus 1. And this p minus 1 is, if it's of exponent p minus 1, then of course it will be of exponent dividing p to the n minus 1. And therefore, this cyclotomic extension obtained by joining a primitive pth root of unity, which is going to give you an extension of degree dividing p minus 1, is fine. I mean, if you get every extension of degree dividing p minus 1 is contained in this ln, because ln contains all extensions, all cyclic extensions of degree dividing p to the n minus 1. And if the degree divides p minus 1, then of course it divides p to the n minus 1. Okay, so that's the reasoning when, of course, you have to assume that you are in characteristic 0. That's when you need a primitive pth root of unity. So that's how it's denoted, a primitive pth root of unity. Okay, so now I've just introduced some notation. What notation? Let's forget everything else, and you have just k, starting with k, you construct this ln, that's a Galois extension, and gn is the Galois group. So of course this gn will act on ln star, and will act on ln star modulo pth powers. So that is one thing on which it acts. I'll call it ln star bar. And this is in general. In general, so general means when the characteristic of k is 0 or p. In both these cases, I can talk about ln star bar, which is ln star, the multiplicative group, modulo pth powers. But if the characteristic of k is equal to p, remember p is the residual characteristic. It's the characteristic of the residue field. So the characteristic of p is either 0 or of k is either 0 or p. So in case it is p, then this gn will also act on ln plus bar. Ln plus means additive group. Bar means you go modulo this Artin-Schreier thing. Where this p takes x to the power p minus x. So, so what is being said here is that, it's being said that they are FP spaces, this and this, they are this in general and this in characteristic P, they are FP spaces, and they are also Gn modules. The group Gn acts on ln star and therefore on this quotient. Similarly, it acts on ln plus and therefore on this quotient. And so this is a Gn module, and it's also an FP space. So what you get are FP Gn modules. So this is, what are these modules? These are ln star bar in general and ln plus bar in characteristic P. Okay, so I have these two FP Gn modules, right? Okay. Right. Now here,
Yes, sir.
yeah, here's the statement that we are interested in. The set of k isomorphism classes of primitive extensions E of k of degree Pn, P to the n. This is a set in which we are interested. This is a set in which we are interested. Primitive extensions of k of degree P to the n. So n is fixed. K is a fixed P field, right? And n is a fixed integer. And we are looking at primitive extensions of k of degree p to the n. This is the thing which we want to parameterize. And the question is, what is going to be the set parameterizing this unknown set? Right? And the theorem says, here it is, the theorem says that this is in canonical bijection with a set of simple submodules D. So I'll explain all this. What is a simple submodule? Of the FPGA, yes?
Sir, why we are using canonical word here? I want to know that what is the meaning of canonical, because earlier we have also used the word canonical. So why we can also say that there is a bijection between these things.
Right.
So I want to know that what is the meaning of canonical bijection.
I understand the question. Right. It's a good question. You see, there is. Let me put it this way. So the word canonical, I'll first explain the meaning by taking an example. So suppose you have a field K, and V is a finite dimensional vector space over K, right? So when you have such a situation, you have what is called the dual of V. And what is that? That is the vector space of all linear maps on V, right? Then you can repeat
Yes,
the process. So one of the things that we know is that this, you might have read it somewhere, that this V star is also a finite dimensional vector space.
Yes, sir.
Over K. And in fact, the dimension over K of this
Both are same.
is equal to the dimension over K of V.
Of V over K. Yes, sir.
Yeah. So in other words, they are isomorphic. If you have two vector spaces, finite dimensional vector space over the same field,
Yes, sir.
then if they have the same dimension, then of course they are isomorphic, but not canonically. Meaning you haven't written down an explicit isomorphism. If you want to write down an isomorphism, then you have to choose a basis of V, and then you look at the dual basis, etc. And then that gives you an isomorphism. But you have made some choices. It's not as if there is it's not there in nature. Whereas if you look at V star star, which is the bidual of V. And now I'm going to give a map from V to V star star. And that is, so of course there's an isomorphism between V and V bidual. Because there's an isomorphism from V to V dual, and then from V dual to V dual is an isomorphism. So obviously there is some isomorphism here, but now I'm going to write down, I'm not saying that there is some isomorphism. I'm saying this particular map that I'm going to write down, so you take an X, maybe I should use this. Take an X here, and I have to send it to some element of V double dual. So that V double dual is the space of linear maps on V dual. So this, let's take an element of V dual, and I have to send it to a scalar. So I send it to the scalar f of x. This is an isomorphism. This particular linear map is bijective, and it is actually a natural isomorphism in the sense that no choices were involved. No, I didn't choose a basis for V and then said, okay, send this basis element to that thing. There's no natural basis for a vector space, right? Except in some very trivial cases where the vector space is one-dimensional, for example. No, not one-dimensional, but is equal to the field itself. Or it's one-dimensional over F2. But apart from that very trivial case, vector spaces don't have canonical bases. But this bidual, I have a canonical isomorphism between V and this bidual. Similarly, when I say that there's a canonical bijection here, what I mean is that I'm actually going to give you an isomorphism which does not depend upon any choices. I'm going to write down an isomorphism between these two sets. That is one of the sets. That's the set I'm interested in. And then there's this other set. This set is what? The set of simple submodules of the FPGN module. So which FPGN module it is will depend upon the characteristic. So it's either Ln star bar or Ln plus bar. So this is in characteristic 0 and this is in characteristic P. And so I have to give a bijection between these two things, right?
Yes, sir. Got it, sir. Yes, thank you, sir.
And the point is that this bijection, it's something which is natural in the sense that it does not depend upon any choices. It is so. Let me show you what the bijection is, or instead of, if you don't really mind, if you really don't want to use the word canonical here, you could say that the following map between these two sets is bijection. So I've avoided the word canonical. It's not being used in any technical sense here. It just means that I have this explicit map which does not depend upon any choices. It's it's natural. I mean, it comes from the nature of the things involved. And the example you should have in mind is what we had done for
Yes, sir. I got it.
For degree P extensions. So here is the same thing for degree P to the n primitive extensions. Okay, but let me explain what the other set is. What is this? What are these simple submodules, and what is the map which is being claimed to be a bijection? So let's explain these things. So, so you know what, of course, I mean, you know that FPGN module that's the same as a vector space, finite dimensional vector space over FP, together with a linear action of the group Gn, right? A group, I'm assuming that you know what is meant by the action of a group on a vector space. So it's just a
Yes, sir.
homomorphism of that group into the group of automorphisms of that vector space. So
GL, L, and bars.
right, GL of that vector space. And what is meant by simple? So simple is, well, here,
Irreducible, sir.
yeah, right.
Irreducible module.
As a representation, it's irreducible. So that means that there are no subspaces apart from the trivial subspace and the whole space. So Fn space V. So these are the only two subspaces which are stable under the action of Gn.
GN.
So Gn, I mean, it's not GLN, right? It is, the group is called G sub n. Huh? And so when you look at
Yes,
the
sir.
definition of simple or reducible, it is a bit like our definition of a primitive extension, right? Why is it a bit like that? Because here, for a primitive extension, what we want is that the degree should be strictly positive. What is it? Maybe I should write
1 or 3.
One. Should not. So that's one of the things. And if I have an intermediate extension, so K, E, L implies that K is equal to E or E is equal to L.
Equal to
That's
L.
what, huh? That's what it means.
Yes, sir.
For an extension to be primitive. Similarly, an irreducible or a simple module is one in which, okay, I mean, simple if V should not be the trivial module. It should not be. That's the first thing that corresponds to this, more or less. And what corresponds to this is that if I have a subspace W, then this W is either 0 or W is equal to the whole of V. So they are actually very, very similar, these two notions, right? So what I'm looking at are simple submodules of, wait, just a moment, huh? So I'm looking at simple submodules D of these FPGN modules. So now I have explained what simple means, but the next requirement is that they should be of degree n. So what's the degree of a module? The degree of a module, I mean, as I said, an FPGN module is a finite dimensional FP space V plus an action of Gn, right? And the dimension over Fp of V is also called the degree of the FPGN module V. So the degree is just the dimension as a vector space over Fp. That word is kind of traditionally used in representation theory. So okay, so that's degree n, meaning over Fp, the vector space should have dimension n. And earlier, when we were looking at parameterizing the set of degree p extensions, those degree p extensions can be thought of as a case n equal to 1, right? Then we were not looking at simple submodules, and we were not talking about degree. We were just talking about lines, FP lines. So that means that the dimension over FP should be equal to 1. And that is what, that corresponds to the fact that n was equal to 1, right? Earlier, when we are discussing degree P extensions, we were looking at FP lines. And this is the correct generalization. When we are looking at extensions of degree P to the n, we have to look at simple submodules of degree n. Okay, finally, so I've told you what this set is. The primitive extensions, and here are simple modules, etc. Now I have to tell you what the map between these two things is. What is the map? I'm saying that there's a bijection between these two sets. This set is sort of mysterious, unknown. This set is completely explicit. So if I give a bijection between these two sets, then I have sort of solved the problem of characterizing this unknown mysterious set. Okay, so what is the bijection? So the bijection is, you start with a primitive, you start with a primitive extension E, and then we had constructed all these ln, etc., right? ln. You can take the compositum of E and ln. Now that will give you an extension of, so here is E, here is K, here is ln, and you can take the compositum E, ln, right? What is that extension going to be? So the first thing to prove, the first thing we will prove is that this E ln over ln is, what is it? Abelian of exponent dividing P. That's one of the first thing that we are going to prove. Of course, this ln to which you adjoin the pth roots of everything in this subspace B, or you adjoin the Artin-Schreier roots of everything in this subspace P, depending upon whether the characteristic is 0 or P, then you also get this is an abelian extension. This is by Kummer theory or Artin-Schreier theory. Kummer or Artin-Schreier will tell you that you get an abelian extension of ln of exponent dividing, dividing is just there, exponent P. So here is another one, and every abelian extension of exponent dividing P is of this form for some subspace D, which is uniquely determined. So the map is that ln, not ln, but E and D correspond to each other if ELN, this compositum, is equal to ln, if it is equal to ln, and okay, so I have to consider two cases, whether it's characteristic 0, pth roots of D, or all Artin-Schreier roots of D. So this is in characteristic 0, this is in characteristic P. So that's the bijection. Okay. So of course it needs to be proved that this is a bijection, but what cannot be questioned is that I have defined a map. Okay, I've defined a mapping, but first I have to, even in order to define this mapping, I have to show that ELN is an abelian extension of exponent dividing P of Ln. And then I take D to be, so since every abelian extension of exponent dividing Ln, not Ln, exponent dividing P is of the form Ln to which you adjoin the pth roots of D or the Artin-Schreier roots of D of some vector space D, Fp space D. So, and with that Fp space is uniquely determined. So I get this map associating D to E. And the point is, or the assertion is, the theorem is that this map E going to D is a bijection. So that's the content of this theorem. And now you see why we were looking at the structure of this kind of a module or this kind of a module as a Galois module. Because we are now going to look for, we are having to look for simple submodules of various degrees. So this is the main statement. Okay. Right. Are there any questions about the statement or?
No, sir.
Yeah, okay. Good. So, yeah, this would have been an, let me just do this number 3 today, and then the rest of it we will do it tomorrow or day after tomorrow. So this is basically, I'm trying to recall in this, what is that? There's some problem. No. Well, there seems to be some problem with the pencil. So I'll have to use my finger instead of the pencil. It seems this pencil is not working. Just a moment. Let me try one last time. No, it's not working. Well, okay, so we'll
Is it discharged or?
yeah, possibly, I don't know. So let me see. Okay, let me try to charge it. Okay, so what I need to recall is, see, we are going to prove ultimately something about P fields. But part of what we had done earlier was something about arbitrary fields. It was a purely, totally algebraic setup, and I need to recall that. So, so what was the setup? Let's see. Just a moment, huh? Okay, so let me see if the pencil has started working. Yeah, it seems to have started. Yeah, good. Okay. Fine. So let's start with an arbitrary field F. Take, I call it the maximal Galoisian extension, but what it means is that you are just taking, this just means the separable algebraic closure. Why do I call it the maximal Galoisian extension? That's because it's the compositum of all Galois extensions of F. Then you get the separable algebraic closure, right? Okay, and I recall that an extension E of F is called solvable if, when I take the Galois closure of E, so you have E over F, then you have the Galois closure, the smallest Galois extension of F containing E, that's a Galois closure. So there's a group, and if that Galois group, this G, is solvable, then you say that this extension E over F is solvable. And of course, it's called primitive if there are no intermediate extensions, right? Now, we have proved that if it's solvable and primitive, then the degree is the power of some prime. So let's fix that prime and let's fix the exponent. Okay. So here is, well, okay. Now, this G is going to be what kind of a G is going to be a subgroup of the symmetric group on L to the N letters. But what kind of a group is it going to be? It's going to be actually a primitive and solvable group, right? If our extension is a primitive solvable extension. Now, if for a primitive, sir, yes.
Sir,
yeah.
Sir, the finite extension E over F is called solvable if Galois group of E cap over K. So what is K here?
Oh, okay. So K is a misprint. You are right. So this K.
Yes, sir. I think F will come up. F will come.
Yeah, this should be F, and this also should be F, right?
Yes, sir.
Yeah.
The solvable primitive. Yes, sir. Yes, sir.
Right. So at two places, I have to replace this K by F. You're right. Thank you. Yes. There is no K here. Because I don't want to use this field, this notation, because that's for a P field. And here I'm looking at an arbitrary field. So let's just continue, call it F. And yeah, there's no K, that's F. Now this G is going to be a primitive and solvable subgroup of primitive solvable subgroup of this S L to the N. And therefore it can be shown that it will have a unique minimal normal subgroup. And in fact, that's how you prove that this is this is going to be a FL space of dimension n. Okay. So what is being done here? So you get so suppose you have what is going on here? You have E over F. Then you get this G, which is the Galois group of E over F, right? From this, you get N, which is a minimal normal subgroup. So what is a minimal normal subgroup? Normal subgroup, you know, but minimal, it's called minimal if it's a normal subgroup such that no subgroup of N is normal in G. What happened? I hope you are still, you can hear me, right?
Yes,
yes,
yes.
Sir, yes, sir.
Okay, good. So now this, yeah. So of course the trivial subgroup of n is normal in G, but apart from that, there should be no subgroup of n which is normal in G, and then you call it a minimal normal subgroup. G, n itself is normal in G, but no subgroup apart from the trivial subgroup is normal. So the point is that when G is primitive and solvable, then automatically there's a unique primitive, unique minimal normal subgroup. Okay? So this n, so as I said, if you let me use a different color so that I can repeat. You start with a primitive solvable extension, primitive and solvable extension. Then you get this group which is primitive and solvable. Then it is a unique minimal normal subgroup. And then G acts on N by conjugation. But of course, what can be shown is that this N is isomorphic to FL to the power N, or I mean, Z mod LZ to the power N. So G acts on this, and in fact, so N acts trivially on N, right? Why is that? Because N is commutative. The action is by conjugation. And if a group is commutative, then the conjugation, there are no inner automorphisms, right? So G acts on N by, G acts on itself by inner automorphisms, and it leaves N stable. And the restriction of that action to N is trivial because N is commutative. So finally, G mod N acts on N. And this, as I said, is FL to the power N. So I get a representation of degree N over FL. And it can be seen that this representation is irreducible. So that is what is being said. What is it? So let me summarize. So you have F here, E here, E tilde here, not E tilde. The notation is E hat. E hat here, and F tilde here. That's the separable algebraic closure, right? Or maximal Galois extension. So let me just call gamma, or gamma the Galois group here. And the Galois group here is being called G. And what is the Galois group here? Here it's G modulo N. And that is isomorphic to FL to the power N. Wait a minute. No. Not at all. It's not this. No. So it's not G mod N here. This is G. That's fine. Then I have to draw a different diagram because I have this normal subgroup N. So I'll have E hat here. Then I'll have E hat, the fixed field of N. And this is, of course, F. So I'll get N as the group here, G mod N as the group here. And this whole group is, of course, G. But remember, this G, okay, Apple Pencil is low. And this, so let me just, You see, this group G is a quotient of gamma. Huh? Gamma is this whole Galois group of F tilde over F, and G is a quotient of gamma. And what you have got is a representation of G modulo N. So G modulo N is, of course, also a quotient of gamma, because G modulo N is a quotient of G, which is a quotient of gamma. So the upshot is that this representation of G modulo N on N, that is an FL representation of degree N, little n, right? So finally, starting from, this is to say that starting from such a primitive extension, what I get is an irreducible FL representation of degree N of the group gamma. This is a primitive soluble extension of degree L to the N. Starting from this, from all these various things, manipulations, I end up with an irreducible FL representation of degree N. The same L and the same N, the same L and the same N, I get an irreducible FL representation of degree N of this group gamma. Gamma is this absolute Galois group of F. Okay, so that is being called rho. So the map sending a primitive soluble extension E of F of degree L to the N to its Galois closure E hat establish a bijection between the set of F isomorphism classes of such E to the set of pairs rho, comma, M. So I've just explained what this rho is. Rho is this representation. So I have primitive solvable extensions of F of degree L to the N. That's one set. Then I'm going to give a bijection with another set. The set of all pairs rho, comma, M. Is it called M or? Yeah, it's called M.
Yes,
Rho,
sir.
comma, M, where rho is what? Rho is an irreducible FL representation of gamma of degree N, and M. M is what? So that is the thing I have to explain next. What is M and what is this map? So there are these two things which I have to explain in the remaining 17 minutes. Okay, so what is M? So it says, okay. So before I do that, I have to say something about rho. So not only do I get an irreducible FL representation of degree N, but its image is solvable. So here for rho, I had to add not just irreducible FL representations, but with solvable image. Why is the image of rho solvable? Because of course, you see what is happening here. So you have F here, you have E hat, N here, this. Oh, where is the image of rho? Anyway, okay, so the simplest reply to why is it solvable is the following. You have F tilde here, E hat here, E here, and F here, right? This G, and this here is gamma.
Gamma.
But G is solvable by hypothesis. Because this E over F is a primitive, not only primitive, but also soluble extension of F, right? So this G is soluble, and the representation, this representation rho that we have defined, it factors through G, and therefore, I mean, since the quotient of a soluble group is always a soluble group, the image of rho is going to be a soluble group. So I have explained what the rows are. In the pairs, I'm looking at pairs where rho is an irreducible FL representation of gamma of degree n with soluble image. And what is M? So here it says what M is. Okay, so and M is an abelian extension of exponent L and degree L to the n of the fixed field of rho. Okay, so just in terms of these pairs, so rho is gamma to, what is it? Some GLN of FL. That's what rho is. So I'll get the kernel of rho, which is of course a closed subgroup of gamma, and then I'll get L sub rho, which is F tilde, the fixed field under the kernel of rho. Okay, so M is actually abelian extension of degree L to the n and exponent L, meaning the Galois group here is Z mod Lz to the power n. Remember, our L and n are fixed, right? Well, where are the L and n? Here. L and n are fixed, right? So I've not yet fully told you what this M is supposed to be. It is I've told you that it's an abelian extension of degree L to the n of n exponent L of the fixed field of the kernel of rho. Okay, so this is an abelian extension here. But there are two very important conditions which this M has to satisfy. I'm not saying anything new here. I'm just recalling what we had done earlier. So the first condition is that M
Yes, sir.
should be M over F should be Galois. And if it is Galois, then you have M here, and you have, what is it? Yeah, you'll have L rho here, you will have F here, and what is the, let me call P the Galois group here. So this is the picture you are going to get, right? So, so the first condition was that M should be Galois over F. I mean, this is Galois and this is Galois doesn't mean that the whole thing is Galois. So I require it to be Galois. And then once it's Galois, there's going to be a conjugation action of, so this, I mean, this group here, the Galois group, is going to be the extension of this by this, right? There's going to be a short exact sequence with this as the kernel, this as the middle group, and this as the quotient. And because this is commutative, I'm going to get an action of this on this. And if you've been following properly, then you know that there's already an action of this on this. Because I'm already given a representation of this row is already, I mean, so to speak, row is in GL of some vector space of P. Let's call it P. Right? So the second condition is that the conjugation action should be equal to the given action. So that is what it says here. So this M is an abelian extension of this L row of degree L to the n, an exponent L of L row. L row is the fixed field of the kernel of row, such that this L has to have satisfied two conditions, that M should be Galois over F. M should be Galois over F here all the way. And the second condition is that the resulting conjugation action of this on this should be the one which is given by rho. Rho already is an action of this on this. Rho is already an action of this. So the requirement is that the conjugation action coming from the short exact sequence corresponding to this tower of extensions here, the tower M L rho F, this tower, right? That conjugation action should be equal to the action which is given to you. Now, this is what we have already done. Let me just end by saying what happens when n is equal to 1. There are certain things which we didn't need to. So here it's going to be what? Primitive. I can omit the word primitive. I just need degree P. It's not P, it's called L now. So if L is equal, I mean, if n is equal to 1, then what I have is degree L solvable extensions of what? Of F. That is the set which I want to consider, right? And here the word, there's a word which is missing, and that is the word which is primitive. Why was it missing? Because if it's of degree L, it's automatically primitive. Right. And we had said that they correspond to pairs chi comma m. Now this chi was a character, right? So characters are representations of degree 1. And we are looking at the representations of degree 1 because our n is equal to 1, right? So that's the same here. I mean, now we are looking at representations of degree n characters. So these characters are representations of degree 1. And we don't have to use the word irreducible because a character is automatically irreducible. We don't have to use the word solvable image. This is automatic because what is the image of chi? I mean, chi, whatever the image is, it's in FL star, and that's a solvable group. and therefore the image is automatically solvable. So you don't have to use this, you don't have to use this. And then the other thing is M was an extension. So it's the same thing. L, we should have called it L chi. F L chi is the fixed field of the kernel of chi. And we wanted it to be just a cyclic extension of degree L. Because a billion of exponent dividing L and of degree L is the same as saying that it's cyclic of degree L, right? To say that if you have a group A which is commutative, and if its exponent divides L, L is some fixed prime, and if its order is equal to L, then of course this A is cyclic of order L, right? So this is what this statement gives you for n equal to 1, and that's exactly what we had proved for degree L extensions of soluble extensions of prime degree. We didn't need to use the word primitive, and we didn't need to use the word irreducible characters, because characters are reducible. I mean, not characters of a representation. These are characters which are themselves representations of degree 1. So they are automatically irreducible, of course, and their image is solvable because you are looking at it's actually even commutative, right? The image, not only solvable. So, and then the two requirements on M are really similar to what we are requiring here. That this should be Galois, and the resulting conjugation action should be the one given by the representation rho. Okay, so next week, meaning next session, which is the day after tomorrow, we will sort of prove this statement. So that was a purely algebraic ingredient. This is the number section 3. Is the purely algebraic ingredients, and day after tomorrow we are going to prove this theorem. Good. Are there any questions? Yeah? No? If not, I'll end this session and see you day after tomorrow.